So welcome to the webinar of 5G-SMART, the webinar on 5G process monitoring in manufacturing. So to which I'd like to welcome you. And so let's see what we have today. So here you can see the lineup of the speakers. So on the left you can see me, Niels König. My name is Niels König. I'm head of Department Production Metrology at the Fraunhofer IPT. And as the next speaker, then we have Andreas Tülich from Ericsson, from the Ericsson Eurolab. He's the program manager for the program 5G for Europe. And then we have Dirk Lange from Marpus Monitoring Solutions, and he's the head of research and development in this company. And furthermore, we have my colleague Sarah Schmidt, also from Fraunhofer IPT, and she's a research fellow in the group Digital Infrastructures. So I'd like to tell you about some rules for this webinar. So first of all, I'd like to notify you that this webinar is being recorded. And this also includes the questions and answers in the Q&A session at the end of this webinar. Then furthermore, I'd like to ask you to please mute yourself if you're not talking. And then regarding questions, so questions are welcome. We would kindly ask you to note down your question and write it in the chat, or use the hand function in the Q&A session. And because we have a tight schedule, and so we have reserved 20 minutes at the end of this webinar just for Q&A. Then furthermore, the recordings of this webinar will be shared via the YouTube channel of 5G-SMART. So what is the agenda for today? I'd like to give you some background and motivation why 5G in manufacturing is important. Then explain you about the 5G Industry Campus Europe. Then furthermore, Andreas Tülich will explain you about how to deploy 5G networks on shop floors already now. And then we have two presentations about two different sensor solutions already solved via 5G from 5G-SMART, from the 5G-SMART project. And both presentations will end with a live demonstration, live from the shop floor. So then we have another live demonstration about closed loop applications. And at the end, we will have the Q&A session. So some information about 5G-SMART. 5G-SMART is a European project coordinated by Ericsson and technically coordinated by ABB. So it's a 2.5-year project and dedicated towards 5G for smart manufacturing. That's actually the project acronym. And it aims at the demonstration, evaluation, and validation of 5G in different manufacturing domains in the industrial fields. So we have applications in robotics, in manufacturing, and also 5G in live production in a semiconductor factory and automation. So furthermore, 5G-SMART aims at the integration of 5G in the ecosystem by the demonstration and validation. And furthermore, we look at how to enhance 5G in future for future applications in manufacturing. So, so for the integration, it aims at business models, both from the mobile network operator side, but also from the end user perspective, so the industrial production perspective. Then furthermore, we look at future-looking manufacturing use cases and how to actually deploy 5G networks with different deployment options. With regards to the enhancement of 5G, we aim at new features like, for example, TSN, but also the TSN industrial LAN integration. Then at different factory 5G network architectures, also with respect to edge cloud and cloud integration and cloud interaction, of course. And then furthermore at network management and configuration. So the project's partners, as you can see on the bottom, the line of the logos is well spread across Europe. So we have partners both from the OT side, but also, of course, from the IT side. So some motivation behind 5G for manufacturing. So why is 5G important for manufacturing? So what are the potentials and requirements? Let's go back in time. So I start with a quotation from Professor Georg Schlesinger. He's a famous production researcher from Germany. And there's a famous quotation from his side: the dividends sit on the cutting edge of the steel, but the speed of these cutting edges is a function of the machines that move them. So on the one hand, this means that cutting processes are still on the basis and also the starting point of many production chains and value chains. And furthermore, there is also an economic factor bound to cutting. So in general, you can say that there is a field of tension between time and cost and quality, of course. That's not new. And of course, some years backlog of production research, there's of course more intelligence in the understanding of production and production requirements. And that's where we talk about integrative production technology. And so it's not only considering the 3 KPIs, quality, time, and costs. It's also about scale, which means that on the one hand, production must be capable for both mass production, but also for mass customization. So which is, of course, quite contradictory requirements. This can be reached with automated planning processes or integrated automated planning processes. What is the solution scenario in order to overcome this so-called polylemma of production technology? It's on the one hand cognitive and self-optimized processes, which is of course also part of the Industry 4.0 paradigm. And this can be delivered with constant process and product monitoring, closed loop manufacturing, and also constant process optimization on the base of data. And here, of course, from our perspective and for the focus of this webinar, 5G comes into this area with the focus of process and product monitoring. So how to align actually 5G in the manufacturing context? So on the one hand, we have all these Industry 4.0 architectures. So this is another layout of these kind of architectures that you can see here on this slide. So it's divided by having a physical shop floor and a data layer. So if you want, it's a cyber-physical production system. On the physical part, you have the value chain, you have the real machines, you have the workers, and you create data along the value chain. So along the value chain, of course, you create parts. And by aggregating all these data, you aggregate also the digital twin, which contains many data along the value chain, may it be simulation data, design data, machine data, sensor data, etc. And in order to connect these two layers, you need connectivity solutions, and 5G is a very promising communication technology in order to fulfill the needs for enhanced flexibility and for more decent process monitoring. So, of course, 5G is attractive because of its unique properties. We know all about these properties already from the many presentations from the press. Of course, we talk about different scenarios. We talk about enhanced mobile broadband communication with high data rates. We talk about ultra reliable and low latency communication with very low latencies and very high reliability. And we talk about massive machine type communication, where you have a high number of devices or high device density. And so with respect to manufacturing, it looks like the most attractive KPI here is ultra reliable and low latency communication, because 5G then outperforms other wireless technologies, especially in terms of reliability, while having also low latency. This is actually the game changer, while 5G is attractive here in manufacturing. So some example in order to underline the necessity for 5G in manufacturing. This is actually showing results from a study we carried out within the International Center for Network Adaptive Production. So we made a factory model, a 3D factory model, where we asked companies from the OT domain how to fill up a shop floor of 10,000 square meter with a number of machines that they envisioned, also partly from their background, very much focusing on machining. And we asked these companies to actually assign use cases to all these machines. So it's not only machines, as we can see here in these boxes. You on the one hand can see different types of production equipment, like different machine types, but also machines from metrology, smart devices, assembly, and also we have some use cases in the infrastructure. And then we have assigned a number of use cases that we can assign to the different machines. For example, vibration monitoring, cutting force monitoring, tool breakage, and so on. Of course, it's clear that all of these use cases cannot be established today because there is no market offer yet. But in case if these devices may be available in future, it's quite interesting to see what is the data profile of this complete production environment enhanced with 5G. That's why we did this kind of mapping. And this is just one example which kind of use cases are assigned, for example, to milling. You see here milling machine, 5-axis milling machine, and we have an assignment of different 5G use cases, for example, wireless vibration sensors, wireless tube breakage sensors, and so on. And then we have a number of how many of these use cases are actually positioned on the shop floor. So I have to add that in total, this 10,000 square meter shop floor is equipped with more than 90 machine tools. And of course, many of these machine tools, so the companies found it very attractive to have them very well equipped with different kinds of sensors. And then we had some requirements towards which latency requirements they envisioned. So is it a critical parameter that is being measured here or less critical? And what is the estimation about the packet size, which is being transferred per cycle? And of course, what's the reliability requirement here? And then we had the overall estimation, and also we could do the positioning of these use cases on the shop floor. And so in total, more than 900 devices assigned to this shop floor. And here you can only see the use cases that are critical for latency, where we set latency requirement below 10 milliseconds. And from this more than 900 devices, more than 200 were latency critical, which is then a little bit characteristic for machining, I would say. And with these data, we can also create different kinds of heat maps. For example, the total number of devices per square, if you want use case density or device density, but we can also calculate the data rates per rectangle and so on. And this kind of data is, of course, then interesting for the radio planning. What I'd like to state here that the total data rate coming from this more than 200 5G devices, the many sensors and so on, the total data rate coming from these devices was more than 600 megabits per second. So assuming that all of these devices are transmitting at the same time, of course, and considering that we have this data rate of more than 600 megabits per second and more than 200 devices, let's say, begging for latency, it was becoming quite clear that there is a requirement for 5G. So because no other wireless technology could fulfill this requirement. Okay, so so that was the first presentation, let's say a motivation for the necessity of 5G in manufacturing. So now I'd like to present the 5G Industry Campus Europe as an innovation platform for the European manufacturing industry. So what is the 5G Industry Campus Europe? It's a very large 5G research infrastructure. So it's a large industrial 5G testbed that we set up here in Aachen. So the 5G Industry Campus Europe consists of multiple different shop floors. And the shop floors are fully equipped with many machines, machine tools like milling machines, turning machines, and so on, but also robots, and also for equipped with logistics equipment like storage, AGVs, and so on. And furthermore, there is an outdoor network of 1 square kilometer that actually surrounds the buildings that contain the shop floors. And this is set up as a 5G non-standalone architecture. And we have this so-called industry spectrum, 3.7 to 3.8 gigahertz. And we are operating this network in this frequency spectrum. So the national regulator has granted the license for the spectrum here on the campus. This is the campus Melaten of the University of Aachen. And as this is a non-standalone architecture, we also have a 4G network as an anchor band running at 2.3 gigahertz. So the project partners are Fraunhofer IPT. Then we have the WZL, which stands for the Laboratory for Machine Tools and Production Engineering, which is an institute, it's actually the largest institute at the RWTH Aachen University. And then we have the Research Institute for Industrial Management, FIR. And network supplier for the 5G Industry Campus Europe is Ericsson. And also we have the fiber network, optical fiber network of the IT center of the university. So we have a funding from the German Ministry for transport and digital infrastructure for this. So what is the vision behind the 5G Industry Campus Europe? So we want to create an entity which is dedicated to holistically explore applications of 5G in manufacturing and logistics. And with the help of the partners and also of industrial partners, so I'd like to emphasize industrial partners, very important, to join and pioneer 5G in industry and help to shape the 5G ecosystem, so which is very important, of course. And we prefer to do this very much application oriented. So we focus on real world use cases, realistic use cases, which actually address the challenges in manufacturing from today. Since we have a multi-tenant environment, we can have a focus single site related applications, but also cross site. So if you want connected applications. So besides the research infrastructure, we also implement a couple of use cases. And of course, this infrastructure is also ideal for carrying out research projects like, for example, 5G-SMART. And the application domains we are looking at, and actually we're talking about 8 different use cases we are implementing here. It's in mobile robotics, it's in logistics, it's in process monitoring, in cross-site processing or cross-site connectivity. It's in smart sensors, but also in data economy. So looking at how to actually exploit data that you transmitted via 5G. So here's a little bit closer look at the different use cases. There is a so-called acoustic emission sensor, which we will tell you more information, more details about in one of the presentations. Then, of course, we look at logistics. It's the classical, let's say, AGV use case. It's on navigation. But since we have indoor and outdoor network, we will test about the transition from indoor to outdoor. It's also on remote navigation. Then the multi-sensor platform, 5G multi-sensor platform, is actually like a Swiss knife for production, which can contain many different sensors that you can apply for either process or product monitoring or machine monitoring. Then 5G blockchain is part of this data economy. It's how to actually safeguard and secure data and have secure data operations, also trading if you want. 5G robotics is looking at mobile robotics, so it's not comparable with an AGV. It's about assembly mostly about of large parts or collaborative robots, for which you need sensor-guided robots, sensor-guided operation, and having a sensor in the loop for the robot operation. It's actually a nice requirement for using 5G. So the 5G cockpit is, if you want, an end-to-end solution in order to access wired and wireless devices independent from the location. So for example, if you have a shop floor abroad and you want to have a look at a certain process inside a certain machine, then you may access a wireless sensor running on 5G, but also the machine data coming via wired connection. And then you have a secured cloud environment and database and visualization in order to make a process monitoring from remote and actually store and visualize your data. 5G 3D is about unwiring an optical 3D laser scanner, like laser light sectioning sensor for 3D measurements. Typically, these sensors are connected with a cable, which is not a problem. But if you get rid of the cable, then it's very easy then to automatically use it with a robot or inside a machine tool. And then it's about integrated process chains, for example, measuring and processing it, a part in the same clamping tool. Then furthermore, we look at edge integration into the 5G network. Of course, it's like an as-a-service hub for the computation of the different data sources and the different sensors, having the cloud and the loop for signal processing, for data processing. And of course, the ambition here is to reach a very low latency for a short time to answer. So now I'd like to show you a video about a project. Hopefully it's not too loud for you. Okay, so I hope you could see the video fluently and also listen to the sound. So I guess you could imagine some of the use cases I described before. They were illustrated and showcased in this video. And of course, we will continue to work on the implementation on these use cases. So in case you want to be informed about what is happening on the 5G Industry Campus Europe, so then there's on the one hand the website, but to be more on a, let's say, day-to-day basis, being informed, you can just follow our LinkedIn site, which contains all kind of information, and also there will be a video series that we are starting soon, the 5G Campus Talk. where we have some more insights about what is happening. Okay, so how to 5G Industry Campus Europe? Of course, companies can address us in order to facilitate and also use the infrastructure together with us and bring your use cases if you want. This can happen on a bilateral basis or in the carrying out of publicly funded research projects. But there's also the possibility in joining the International Center for Network Adaptive Production, which I've already talked about. So it's looking on different fields of application. It's holistically looking at digitalization in production. So as you can see, sensor systems, data acquisition, interface and connectivity, data synchronization, middleware, data modeling and analytics, digital twin and production life cycles, cloud system, IT architectures, and digital business models. Okay, so so that's the information about the 5G Industry Campus Europe. So now Andreas Tülich will tell us about how to actually set up the 5G Industry Campus Europe and also other networks in production. So please share your screen, Andreas.
Thank you, Niels. I will try to do that immediately. Give me a second. So does this work for you?
Yes.
Looking okay? Good. And I hope you can hear me loud and clear as well.
Excellent.
Perfect. Then yeah, once more, thanks for the invite, Niels. For all the others, my name is Andreas Tülich. I'm part of the Ericsson R&D. I'm based in an R&D center of Ericsson in Germany here called Eurolab. That is the R&D center nearby Aachen here in Germany. And in my role there, I'm currently head of the 5G for Europe program. And in this program, we have been asked to look particularly into use cases beyond mobile broadband, use cases beyond the normal smartphone users, like all of us. And we said we're going to focus in particular on production and manufacturing industries. And as soon as we detect there a topic that today couldn't be solved, or hasn't been solved in any satisfying way, that's the point in time where we start getting active. That's the point in time where we really start to make an effort, get our hands dirty, and where we do it for real. And this brings us right away to the topic of today. It's called 5G network solutions for shop floors. And therefore, let's get into it and have a look at an example of a shop floor. What you see down here is a typical shop floor. You see some inbound, outbound logistics. You see some warehouse, some storage. You see certain production lines. You see production islands. You find robot cells. You find some process machines and quite a few moving objects. It could be the standard forklifts. It could be an AGV. It could be this tugger train or Routenzug, as we say in Germany. Or I guess there was even a flying drone here on this picture. So all these movable objects. And what we see as well here on the top is that there is a team that is running this shop floor. It's usually the shop floor management. It could be the machine operator. And these guys up there with their systems, the MES ERP systems and the IoT platforms. What we learned is that these guys are absolutely not satisfied with their current view into their shop floors, with their current insights into their shop floors. They all claim, they all stated to us that this is by far insufficient. Why is that? Usually, typically, these shop floor managers, they're requested to boost the capacity of a shop floor, let's say by another 30%. I guess all of us can easily imagine that you can't do this or reach this anymore by just optimizing some production cycles by 1% or 2%. They need to look into entirely different topics. And for them, for example, shop floor logistics is a huge topic, is a key topic. And for that purpose, they need to have an insight, near real-time digital insights to their shop floor. They are basically dying for that. And they need to understand, where are my components? Are they in the warehouse? Are they in transition? Is an AGV available? Can they deliver certain components to my assembly line, to my assembly cell, to my robot? which HVs are available, which machine needs to be calibrated, which battery needs to be recharged, etc., etc. So all in all, these guys, they want to have this near real-time digital insight to their shop floor, far beyond what they have available today, to be able to live up to this expectation, to boost the productivity, what is needed. And by providing such an insight, with, for example, numerous sensors, numerous gateways that are wirelessly connected on such a shop floor, you gain a certain visibility. You, for the first time, get data. You get different insights what you've had before. You may even get in-process insights. And this visibility allows you to translate it, to analyze it, to do a prediction of what is going to happen next. Which machine will be idling, which machine will be congested based on the new data that you got. This might be by an expert doing it, it might be by an algorithm, it might be by artificial intelligence. We're probably going to see all of these different variants. Then, once you have reached this state of predictability, the next step would be to adapt, to really steer, to take the conclusions and manipulate, steer, adapt, or change your process on the shop floor. And we have taken our example from the logistics. If we get a bit closer to the topic of this webinar today, it's about in-process monitoring. That is pretty much following the same principles. You want to have a near real-time digital insight into your process. And you would like to get as deeply into your process as possible, meaning you would like to place sensors, ideally on the product under production. You want to place it on the clamp that is holding the product, or you want to put it to the tool holder to get as closely to the place where it's going to happen, to get precise data, real data, and also data with no delay. And with this deep insight into your production process, this in-process monitoring, you get the visibility for your production process. By applying then your algorithms, your tools, your IoT applications, you can predict, you can adapt, and you can steer back your processes at the end in real time. And that is where you have the closed loop application. And now we're entering, so to say, the masterclass of network adaptive production. This is the place where you really need to be absolutely sure about that you receive the right data, you receive it in time, you don't lose it, you get it without any latency, and you can steer also processes in real time. This is network adaptive production in its best, I would say. So what do we need to achieve this? I mean, it's a couple of dotted lines called 5G here, which is easily done. And to be able to deploy such a scenario, you need a sort of 5G ecosystem. And what we see here is that you will have a need for a 5G non-public network as it's defined by the 5G SIA, which is depicted on the left. You see a sort of network in a box, and you see a couple of radio examples that could be typically deployed in an indoor scenario. And this 5G non-public network that would northbound, so to say, connect to the MES ERP and IoT platforms. At the same time, this 5G non-public network, it would operate on licensed spectrum. And last but not least, on the shop floor, you will need what let's call it sort of industrial smartphones, 5G industrial gateways and sensors. This altogether makes up for a 5G ecosystem, and let me walk you through to a couple of these elements now in a minute. Let's start with the 5G non-public network. That's a typical example on how such a network could look like. On the picture you see it's a sort of 5G network in a box. It's fully self-contained. It's a complete mobile network in there. And if you see on the left-hand side, you see that it's an enterprise core server that is hosting the fully virtualized 5G core network, with all its functions. Additional server that could be in there, we call it multi-purpose server, that could host dedicated enterprise OSS customized applications. It could be critical push-to-talk services, grade-of services, any other service you could imagine, in addition to the enterprise core functionality. The router 6000 is there for IP connectivity among those elements in that, and it's also the, so to say, connectivity to your IT infrastructure, to your industry cloud, your enterprise cloud, on-premise, whatever you might have. On top, you see 4G, 5G baseband, That is the unit that is the brain of the radio, and that is then connecting to any of the radios out of, for example, the Ericsson radio portfolio. And we have just cherry-picked here a few ones that could typically be deployed in an indoor scenario. It could be the micro radio, or it could be the radio dots, which would then be connected to an indoor radio unit. And in here, this case, it would be up to 8 dots per one IRU that could be connected simply by a Cat6 cable, Cat6 wiring. This network that will be operated always in a licensed spectrum. And talking about licensed spectrum, I've taken a picture here from Bitkom from 2018, which is still absolutely valid, and it shows that there is quite some continuity in the spectrum allocation. What you see here is a segmentation into low band, mid band, and high band. The low band you may all know from the good old days of GSM, for example, in the 100 megahertz domain here in Germany, for example. This is spectrum usually operated on FDD, frequency multiplexing, and typical bandwidth of 2 times 10 megahertz. Very, very good spectrum to have for cells of a size of up to 10 kilometers. And with a certain downlink and uplink speeds that you can see here. The midband, you probably recall from the LTE days, typically in the 2.6 gigahertz area, 2 times 20 megahertz FDD spectrum has been allocated and is used by most of the operators here, for example, in Germany. 5G is a lot about new spectrum, meaning that the existing spectrum, low band, high band, or low band and mid band, could be partly utilized for also 5G NR. But in addition to that, we see quite a bit of new spectrum coming up. Talking about new spectrum, you see here on one side a 3.6 gigahertz spectrum, typically 100 megahertz bandwidth, which is a TDD spectrum, time division multiplexing. And that has been just recently auctioned here for countrywide, nationwide networks and acquired by the different operators here in Germany. In addition to that, the government has, excuse me. Sorry about that. In addition to that, the government has allocated additional spectrum of 3.7 to 3.8 gigahertz for local usage. And that is what Niels König has explained is being utilized, for example, here at the 5G Industry Campus Europe that Niels just introduced. Above 6 gigahertz, there will be spectrum available, or is spectrum available, which is called high band or millimeter wave, typically in the area of 26 or 28 gigahertz. What is not listed here, there is a new spectrum coming up, probably in the area of 42 and 60 gigahertz. And this is spectrum that is used for really, really small cells, for local deployment, for cells where you have really, really high demands on bandwidth, for example. And if you remember the spectrum model of Niels that he summed up there to quite large numbers of devices and quite large number of bandwidth, that could be also then additional deployment next to the mid-band, next to the 3.7 to 3.8, could be an additional deployment to satisfy those needs in the high band. So 5G, a lot of spectrum is available, a lot more becoming available and opening up for entirely new scenarios. If we look then at the deployment options that we have, and I've taken here just an example from a white paper from the 5G SIA, which I recommend you. It's there's a link is here. You also can find it just by googling it. 5G SIA has sketched a few scenarios. The one extreme is a standalone scenario, fully self-contained. That's what you saw on the picture. It's the self-contained box, everything included, including the radio, that would be deployed locally with an enterprise. That's the one to the left-hand side. On the right-hand side, you see the scenarios that the service would be provided by a network operator. And there you will see different flavors. It could be that it's just an extension of the nationwide network of the operator to an indoor shop floor, and it could be also various flavors in between. If we zoom into this for a minute, is the fully self-contained isolated deployment is depicted on the left-hand side. You see in the black box, it's the fully self-contained network that can operate on its own, which could be deployed locally, could be operated by a network operator, by a service provider. And also it's the opportunity here that it could have a connection to the public network services. That it could utilize, for example, indoor, that private network, non-public network, and when leaving the industry campus, then utilizing the macro network. On the right-hand side is the other end. The other extreme is that you take the existing public network of the network operators and you extend it by just the radio cell into the industry part there. And then if you look at these two extremes, you can easily imagine that there are many, many different options in between. For example, like here depicted on the next two figures, you could, for example, share the radio on the left-hand side. Here you have one radio that is utilized by the enterprise network as well as the operator. For example, you could offer the operator services to the smartphone users on the campus, while at the same time offering the industry services that you are planning for. On the right-hand side is another flavor of it, where you also share the control plane, as said, all very nicely described in the ACIA white paper. Niels asked me to do a quick zoom into the radio layout, how that could look like, and I've chosen here the radio layout that we have chosen here on the campus. It's the Fraunhofer IPT. It's one of the shop floors of the halls here that we see. And it's a very, very densely populated shop floor factory hall of around about 3,000 square meters. You see that the dimensions here. And that one we have covered in this case with radio dots. It's those little yellow elements you see on the ceiling. And we have just mounted them on existing elements at the ceiling. It's a height of, I would say, 4 to 5 meters probably there. And for that entire location, we have deployed 8 dots to cover the entire shop floor. The beauty here is that they can be easily mounted. It's just a click and then they are mounted. And the wiring is equally easy because it just requires Cat6 cabling. And that includes power and everything as well. So that can be easily achieved and rather quickly done. Going one step ahead, going back to the 5G Industry Campus Europe, you have seen this picture from Niels. It's those area that the entire area that is covered outdoor. We see 3 indoor shop floors that have initially been covered. A 4th one is included as well that is outside of this campus, it's 2-3 kilometers away. And what is important for this Industry Campus Europe are in particular 3 elements that are listed on the bottom. Is for this 5G network solution, we have chosen an architecture that guarantees the separation of concerns of each legal entity. What does it mean? Each of those indoor shop floors, they want to own their own data. Any data that is generated locally stays locally, and that is generated locally and consumed locally stays local, and is not mixed up with any of the others. All this is inbuilt, guaranteed into the architecture. It also allows all the indoor users to roam into the outside network. Still, the data is then falling out of the network element on their indoor installation. And also, of course, it can visit the neighboring indoor shop floors if wanted. And of course, what we have done here is that we started with 4 indoor shop floors. It's done in a way that it can be easily expanded to cover additional indoor networks. That is what I planned to present as a quick glimpse into how such a shop floor deployment could look like, what we have done so far, why we have done it, and what we have considered in setting this up.
Okay, thank you very much, Andreas. So, very interesting insights. So we have to step to the next presentation. So I asked Dirk, please, to share his screen. So Dirk will speak about acoustic emission sensors. What is acoustic emission, Dirk?
Can you hear me now?
Yes, very good.
Okay, thank you. Yeah, hello everybody. Nice to meet you here virtually. I want to talk about a little bit about wireless acoustic emission sensors, what we are doing in the 5G project. First, a small introduction here. In what field we can use this? We saw a lot of 5G now. We are more in the area of production parts. Later in the second presentation, I will give some more information about the products and systems, sensors. But we see here we have different approaches or different challenges. For example, we have very big parts where it's hard to mount some sensors. We have big parts for the on the right side here on the for the automotive, not automotive, but train production wheels. We have here very cost-extensive parts for the turbine blades, cost about a few thousand euros such a part. So we have very high cost, not only in material, but also in production time. So there is a need to get deeper, to get closer to the parts, to the cutting process. And one approach is, beside other sensors, to use acoustic emission sensors. That is a very sensitive quantity. And the principle is here on the left hand. You can see that the cutting edge could be a grinding wheel, could be a milling tool, a turning, cutting edge, whatever. If metal material is cut, you can see you have a kind of a chip breakage. So the chip is cut out of the material, and this produces some very high frequency noises. The frequency range can be from the lower kilohertz range to multiple megahertz, to 4 or 5 megahertz. That depends on the process, on the material, on the machine, on the damping and filtering. So we have a kind of forming process producing these acoustic emissions. These acoustic emission waves then run through the material, could the workpiece clamping, or the machine table, and then there is a state-of-the-art acquirement using piezo quartz, piezo ceramic to acquire or to get these data. And then you have these structural vibrations. You can see here some example signals. It's sometimes very noisy, and it's a challenge to get the right information out of these signals. So the principle here is on the left hand. You can see a kind of acoustic emission sensor. The principle is very easy. It's a piezo element. You can find these elements in greetings cards with playing music. It's the same principle. And it's using vice versa. You have a damping mass, and every wave which comes over from the cutting process over the surface goes through the membrane, through a coupling element in this piezo. And then you create some signal changes, some loads with a load amplifier. You can get a very high sensitive signal. You have different kind of sensors, and for example, you can see on the top side sensors which are mounted by screws. Other, you have some small inductive coupling, but you can see here the disadvantage because the distance between the sensor element and the emitter or transmitter or receiver is only a few millimeters. So there is often a need or a problem to install or integrate these sensors. For example, here on the right hand, you can see some grinding applications where the signal flow could be through the grinding wheel, through all the bearings and on the spindle head. And that can cause a lot of problems because you have damping, you have noise from the bearings. And so that is only one of a couple of examples why we want to have or want to develop some 5G acoustic emission sensors. So that means we have a wireless monitoring. One other application is a tool breakage. We have data rates up to 10 gigabit per second if we do not have any pre-calculations. So we produce a very high amount of data. But in this project, it's also a challenge to find or an idea what is needed for the pre-amplification, pre-calculation. Yeah. Here is one example from the IPT where the position is resolved in the independence of the amplitude. So all over the surface machining, the frequency or the signals of the acoustic emission band was sampled and then visualized in these kind of a map, position spindle and position Z and the magnitude. This can be used, for example, to detect in cost-intensive parts or critical parts like turbine blades or blisk to find some deviation in the during the cutting. So when we look to the use cases, we have, for example, tool breakage detection and metal cutting processes. That means we want to monitor, for example, very small tools in the sub-millimeter. And if we see to the PCB production, there we have sometimes 100 or less than 100 microns diameter. We have multi-spindle applications, material contact, gap control and grinding. That means we can run with a fast speed to the workpiece and then stop when we detect the contact, collision monitoring, or crack detection during grinding. It also produces some high frequency frequency signals. So as you can see, there is a high need, and it's also a challenge because these acoustic emission sensors signals are a very high frequency including. What is a typical chain? When we look back, acoustic emission is known since 30 years, and there is a standard measurement chain. We have the high-pass filter, we have an amplifier, then we cut the upper range, the lower range, and in the end we have some RMS connected or collected is converted with the analog digital converter and then provided to Ethernet. This was done in the project. We used an RE sensor board developed and connected it as a prototype with a prototype to the FPGA board, where we are more flexible to find some more algorithms, better filtering, faster filtering. So in the project, we connect the RE sensor to the sensor preconditioning module. In the end, it's a complete hardware module, high-speed analog digital converter up to megahertz. We have FPGA or signal processors. We have some connectivity interface to get or to write out the signals. For sure, we need some as well as some onboard memory. So that looks a little bit big, but every big thing starts with a little bit bigger development. We have here on the left hand the acoustic emission sensor, an analog board, and the FPGA board, and write out the data to the Ethernet. And in the end, we want to close this loop to use this sensor device as a prototype inside the machine and send out the measurement data stream. We can configure the data or configure via data that is not so with high data rates. For example, we can want to change the filter, the sampling rates, and run some fast Fourier transformations. So I think that is a combination then, also a little bit the structure for the machine, not only the R sensor module, we transmit the data to the station of 5G core, we can have a data processing in the cloud, maybe a parallel analyzation of the data, and then we want to send back the data via a monitoring unit to the machine where we need the real time. So we have then later a closed loop if it's needed via the 5G interface. The other thing is we can save the data within a database or an edge device. So I think now we can hand over to Niels to your practical demonstration, or?
Yes, thank you very much. Can you please stop sharing your screen?
Oh, sorry. Yeah.
Otherwise, people cannot see what we are doing here.
So.
Yes, that should work. Okay. So I hope you can see me now. So I'm handing over the camera to my colleague Maike, and I'm switching sides. Okay, so as you can see now, I changed position. I'm now on the shop floor of Fraunhofer IPT. And I'd like to show you this kind of tool here. This is actually this type of cutting edges that Dirk was referring to. So during the machining, these cutting edges are worn out, so they break out, for example, but also the complete tool can break in the worst case. What we then do is we can analyze the cutting edge. In this case, it's a camera-based solution where we have quantification of the toolware, and these orange colored areas are actually automatically recognized by a neuronal network. So there's some artificial intelligence behind it. But of course, this is nothing we can do during the process. And for the process monitoring, the in-process monitoring, you just follow me. Okay, so we have the demonstrator that Dirk was explaining. So we have this electronics that you have seen in the photograph. So here's a little bit more compact version. So we have some pre-amplification and signal conditioning PCB, and then there is an FPGA board. The FPGA board then generates the signal spectra. So there's an FFT calculation running at this 1 megahertz signal. And then we have the transmission via Ethernet into an industrial 5G gateway. So from here on, the signal is being then transmitted via 5G, of course, then handed into the intranet, so on the shop floor LAN, and coming back via Ethernet. So there's some cable coming back here, and there's some industrial PC inside this box. And this PC is showing actually the result of the signals we are creating here. So here's the piezo sensor attached to the sensor electronics. And now if we create, now it seems to be, okay. Seems not to to work, unfortunately. Okay, I'm sorry. Okay, it worked. It worked 1 hour ago, actually. So what I would have shown you, it's just a software problem. Shown you is a waterfall plot where we have on the x-axis time, and then on the y-axis spectra. And you can actually see then how the cutting edge carves into the metal and scratches the metal. And on the one hand, you can hear it with your ears. On the other hand, of course, we create data coming from this process. And in our case, as soon as a certain amplitude is exceeded, then it interrupts the voltage just for the sake of the demonstration. And yeah, that's just an example of how to react on these kinds of critical process conditions. If you wonder about the background noise, that's because we are actually on the shop floor, and all the machines and all the colleagues working here. And so with that, I'd like to start a small break. Since we are running a little bit behind, I would say 3 minutes, and we meet back on 15:06. Okay, so welcome back. So let's continue with the program. I asked Sarah Schmidt to share her screen and tell us a little bit about the multi-sensor platform concept.
Thank you very much, Niels. I hope everyone can see my screen and hear me. Yes, welcome back after the short break to the 5G-SMART webinar. My name is Sarah Schmidt, and I now give you a short presentation about the 5G-enabled multi-sensor platform for process and machine monitoring. So if we talk about the vision we have of our factory of the future, we see a lot of challenges and requirements. More and more demanding processes are in industry, and also the wish for individualized products, what means that we also have more and more different processes that are more and more demanding. We have the need for a versatile and scalable real-time monitoring of production and processes, and not only for optimization and understanding of the processes and products, but also to be able to handle dynamic configuration changes. And if we want to create something like a digital twin, we need an all-embracing, complete documentation of the production. So all this can only be reached if we go into a digital transformation for industry. And that means that we need highly efficient, connected, and flexible factories of the future. So a perfect match between sensors, communication, and computation modules. There are, of course, already solutions and technologies in the industrial world that try to make this vision reality, but still all of them have their weak points and bottlenecks. For example, many connections are still wired, mostly Ethernet and field bus protocols, and of course they have a limited flexibility, sometimes are even impractical to deploy and have a high cost of deployment. We also have wireless solutions like, for example, wireless over link and wireless HART, but they need to be more flexible and especially more sensor diverse. Standards as Wi-Fi and Bluetooth, they don't meet reliability requirements, especially not in connection with reproducible latency. And all of those connections are mostly point-to-point connections, what of course, again, inhibits flexibility and a simple management. And actual sensors we have are mostly separated standalone systems. So we have additional effort to route data to centralized computation services, and the interoperability between machines is restricted. So having a look at current multi-sensor platforms we are aware of, most of them just focus on a certain application and don't have a very broad spectrum, and they have a limited real-time capability. And at least existing infrastructures are mostly unable to support demanded network density, especially when you think about a very high interconnectivity between a lot of machines or sensors. So actually to overcome those weak points and to meet the requirements of the future, of the factory of the future, we came up with the following objectives that such a multi-sensor platform has to fulfill. So first of all, it has to be a compact and modular device that can contain multiple sensors. For example, acceleration, gyroscope, and so on, whatever is suitable for the application. Then it has to have IP68 standards, so it can be used in a workshop environment. And we want to have something like brownfield digitalization for machine tools. So that means we improve the existing machine and infrastructure and work with the capacities we already have. For an industrial solution, it has to be flexible and scalable. So we aim for smart sensors and for processing in the edge cloud for scalability. To facilitate maintenance, such as software upgrades, for example, we want to have a centralized device management and deployment of configuration. And at last, to really have a flexible and easily integratable device, we want to have a wireless connection. So possible use cases and applications for such a multi-sensor platform would be the monitoring of various process parameters, the track and trace of pallets or products in intralogistics, and a continuous data storage of full documentation as a digital twin. For the wireless connection, we will take 5G technology due to the fact that some requirements like real-time capability, also the possibility to scale to a large number of devices if we are talking about high interconnectivity and therefore also sensor networks, and concerning high data rates because of a lot of sensors, and large number of devices which all simultaneously have to transmit data. Those 3 points and requirements can be fulfilled via 5G because of the 5G key performance indicators that are MMTC, URLLC, and EMBB. And on top of that, the localization, which will be available for indoor for 5G in the next years, gives us the chance also to match position data with process and sensor data to really get a complete digital twin. So such a multi-sensor platform could be used on a shop floor at different places. So not only on the workpiece itself, very close to the workpiece, but also in machine tools, in machines and on the infrastructure. So if all those parts are equipped with a multi-sensor platform, they are connected via 5G to the 5G factory cloud, where the data can be processed and stored. And there's a feedback loop from the 5G factory cloud on one side to the machines, for example, control, and on the other side also in form of configuration data to the sensors. If we try to fulfill such a flexible sensor platform, we face, of course, some challenges. The first 3 points, what is to fuse heterogeneous data on the shop floor, to also synchronize all those different data streams, and to have a communication architecture that is completely optimized for real-time control. Those are points where 5G is a game player because it provides a reliable and scalable network. So the processing, the data could be integrated easily. It provides a timestamping, so we have a Korean timing over 5G. And concerning real-time capability, of course, the multi-sensor platform itself has to be real-time capable if the whole system has to be. So here also 5G gives us the URLLC feature. And another challenge we have to face is, of course, the centralized device management to really facilitate handling. So we have to realize reconfiguration possibilities, firmware updates, enabling, disabling sensors, and all of this in the best way remote. The multi-sensor platform's functionality itself can be divided up into 3 steps that are digitalize, delegate, and dispatch. Digitalize means that each physical quantity has to be turned into a digital information as soon as possible. And here we have actually a trade-off between deciding if we send raw data, which allows for flexibility later, but it increases the energy consumption. And on the other hand, if we try to lower the energy consumption, for example, with pre-processing on the shop floor device, then it may affect latency. So at this point, we decided to leave this trade-off as a tunable configuration. So it can be adapted for each application. Delegate means then that the data stream is delivered to the factory cloud so that we have the chance to exploit full flexibility and scalability of software services. And dispatch means that the factory cloud is not the endpoint because there's a control loop for the sensors and the machines in form of configuration, data, or control. So considering those 3 steps, digitalize, delegate, and dispatch, the whole systems has to look as the following. We have an embedded device on the shop floor, we have the 5G link for real-time capable transmission, and we have the factory cloud for scalability and flexibility. If we now look at concerning those steps, the multi-sensor platform's design has to look like the following. We have 3 blocks. There's the field sensors, the local processing core, and the 5G modem, where the local processing core and the 5G modem are a reusable unit, so they are always the same for each multi-sensor platform. The field sensors instead can be chosen concerning the quantities of interest for the application, so they just have to be suitable for the applications, and there are different implementations possible. The local processing core can be updated and configured from the factory cloud. And as I already mentioned, IP68 standards, so each unit has to be waterproofed to confidently operate in a workshop environment. Taking a look at the local processing core, we have a trade-off between compactness and low energy consumption via power and versatility. But for sure, it has to be a high-performance embedded microcontroller, which has some serial interface buses C to the field sensors, and on the other side, USB or Ethernet connection to the 5G modem or 5G device. The field sensors itself should be digital transducers or based on digital integrated semiconductors. They have an auto-discovery functionality, what means that they can automatically be found by the centralized device management, so you actually know which sensor is at the moment plugged in. The field sensors have the same interface for data power and control paths. And we decided on internal and external sensors. So external sensors are those which sense the process and on the shop floor. And the internal sensors are integrated in the embedded device and they sense the environment. So they monitor the multi-sensor platform's condition. At least the 5G modem should be integrated in the embedded device, but there should also be the option for an external connection in the case that it's incompatible with electromagnetic propagation. And the 5G modem gives us the time synchronization, so that means that the information stream can be correlated directly during the process. So as we now saw, we have the embedded device on the shop floor. And to complete the whole system and the 3-steps approach, we include now the 5G link and the factory cloud. The 5G link gives us a low latency of a few milliseconds and a high reliability. It provides a bidirectional way so that we can stream data up into the factory cloud, but also can get configuration data back for the sensors. And 5G gives us the capability to connect to a large number of devices. For example, if we talk about a lot of devices for a sensor network on a shop floor. So the factory cloud shifts the task from the embedded device towards high performance processing servers, also due to the energy question, and it is the central coordination point. So coming to a summary, the multi-sensor platform device combines an embedded device on a shop floor, the 5G link for real-time capability, and local computation capabilities in form of a factory cloud for flexibility and scalability. It is an adaptable and flexible system in a modular design, so it's customizable for each process. It provides connectivity of different sources and facilitates routing of data to computational services. It features time synchronization and gives a centralized management system. So all in all, it's a powerful tool for high performance process and workpiece monitoring, and therefore a perfect match between sensors, communication, and computation modules. So with this, I would like to end with this short presentation. Thank you for listening, and Niels Koenig will go on with a live demonstration on our shop floor at IPT.
Okay, thank you very much, Sarah. So let's change sides again. So hopefully this time works better. Okay, so we have here one example about the 5G multi-sensor platform. This time equipped with a accelerometer, which is actually also a piezo-based element. From the principle, it's comparable to the acoustic emission sensor. This time, the sampling frequency is much lower, so we have a sampling frequency of 20 kilohertz. And then we have some sensor electronics, so there's also PCB with an ADC and some preamplification. And then there's a microcontroller attached, and we generate the measurement data as UDP packages, then being transferred to the 5G gateway. There's a bridge in between because our sensor does not understand DHCP. That's a little bit of an ugly thing here, but nevertheless it works. And what we do here is actually a monitoring of the vibration of this workpiece. So this kind of workpiece is called BLISC, Blade Integrated Disc, and these are being milled with a 5-axis milling process. And as you can see here, we have this couple of these blades, which can easily start to vibrate during the milling process because it's very thin-walled. At the same time, you have a very complex geometry, and of course, it's a safety critical part. So you do not want to have any flaws on this part. During the milling and during the vibration of these blades, you may happen to have a vibration mark, which is actually a waviness on the surface. It's just because of that the blade goes away from the milling tool's cutting edge, and you want to actually avoid it. You can only avoid it if you know that you have this kind of vibration. And when you excite these kind of elements, you start to hit some resonance frequencies, and that's what it's about. So you need to detect when you hit with this milling process and excitation and resonance frequency. I'm giving you an example how it actually sounds like if these kind of components are being milled in the milling machine. You have to imagine it's being milled from one piece of titanium. It's a disc, so it's being milled from one piece of metal. And you can imagine from this geometry, it's quite a complex milling operation and takes like 40 hours to complete this part. This is a small version of this part. Typically, it's double that size. So the sound of the part in the machine actually sounds like this. Hopefully you can hear it. And you can see actually the vibration spectrum coming out of this part. So there's some kind of loudspeaker under this component. So we induce this kind of vibration artificially. And you see that there are some frequencies are dominant. And you can imagine this is actually a resonance frequency. So during the monitoring, of course, you analyze these kind of frequency patterns. And in case you notice that you hit a critical resonance frequency, then you just simply send a command to the machine to increase the spindle velocity, and then you get out of this resonance window. So that's actually the story behind. To make the story also complete, let's continue again this demo. So we fixed the problem in the meantime. So that was actually, we had a broken FPGA board, which we had to exchange on short notice, and that's a completely different model. So, and it's not really running stable. So it's about shaping the ecosystem, and sometimes works, sometimes not. Now let's start the drilling machine. So here's a drill which we have artificially outworn. So we grinded the cutting edge. So you will hear this from the sound when we hit the metal. So it's an ugly sound. Hopefully you still hear me. And if I increase the pressure, you see in the waterfall plot, you see the cutting edges contact with the metal. And in the false color, you can see the amplitude actually. And on the on the y-axis, you see the spectrum from 0 to 500 kilohertz. Okay, so now we finished this, and then we go over to the next presentation from Dirk, and Dirk will explain us about how to close the loop. Please, Dirk, share your screen.
Yeah, thank you. So hopefully everybody can hear me.
Yes.
Okay, thank you. Yeah, I want to show you how we close the loop, and hopefully we can give some practical demonstration here. Sorry. So what we are doing here, for short introduction, Marpers Monitoring Solutions, we are partner of the project, and we are working on in the case of sensors, monitoring systems, databases, adaptive control. We have such specific modules where we monitor the process. You can see here the graphics, and we have a couple of sensors we integrated in our system. We adapt to the control, and we also have sensor or tool holder integrated sensors. In the last years, the field grows wider and wider. Was in the beginning only sensors and monitoring, and now we have to adapt to networks, to 5G, and so we think there is a very high potential also in different kind of industries here. So where are the applications for the monitoring? We have a wide range at the machine tool. We look for workpiece and clamping. That means we have incorrect clamp parts. We have ships between. That means we will have damage eventually in workpieces and tools. We have raw and inhomogeneous. Then we have a wide range of cutting tools. We have wrong program. We have influence by override. We have manual operations. We have chip and jam. We can have problems with coolant lubrication. We have loading, unloading. That means collision, wrong positions. We have problems with the cutting tools, for example, as I explained in my last presentation, broken or missing worn tools. Machine operator is also a big influence factor, or when you look now to modern plants, there is one operator dealing with 10, 15 different machines. So there is more need to give him help with sensors, with support systems or intelligence systems. We look to quality. We do want to avoid part verification, where there's a need for process documentation. That's also in the, I think, 5G surrounding. We want to grab data from the machine and get it quickly to other machines or to the central server of the plant. So you can see here also, besides condition-based monitoring, there are a big variety of applications for the use of sensors and 5G. That is a picture I showed already in the last presentation. Different parts, big parts. When you see here on the left hand, I can show here. This is parts in the aircraft industry. It needs sometimes 20 hours to machine, and so there is a need, if something happens, to detect this very early. Yeah. The other parts here are, turbine blades. This is for the windmill industry, big gears. So other requirements is the use case machine protection. Here you see some bad examples. It could be sometimes only a tool holder which damaged and crashed the material, but you can have bigger damages here. Two spindles crashed into each other because of a programming error, or here a big workpiece holder crashed, and there is an idea to avoid this with the use of sensors. That is use case machine protection or collision monitoring. Then we have vibration monitoring, as Niels already showed. We want to detect the vibrations. As you can see here, we have a lot of signals. We have three-dimensional sensors with acceleration, with velocity speed. And there is a high demand to make analyzations, FFTs, in the higher kilohertz range. Other application, I hope you can see the video, is the adaptive control. That is meaning with closing the loop. There we measure, in that case, the spindle power, but the principle is usable also for other quantities like vibrations. I will show later. Yeah. So the idea is, when I have less load, I can increase the speed in a reasonable range, maybe between 70 and 130% of the override. This is here a milling process. The one requirement is to make the process more stable. and to run it faster or to prevent from tool and workpiece damage. When you remember these big parts, machine 20 hours, and then at the end you have a problem with the tool and all the total part is scrapped, then you have a very high amount of cost. So that is one approach here with the adaptive control. Sorry. Yeah. So as you can see, you have a lot of advantages, or our aim is to have more advantages in use of 5G. We have applications we can now deal with standard sensors, but we see more the requirements to have wireless sensors for gap control, for collision monitoring, measurement in very big machines. There is not possible to use cables with 30, 50 meters, or it's a very big effort to make a retrofit on these machines. So it's good to have something easy installed which can send the signals wireless. Then what we see more and more important also during this very hard time with the COVID, that we have sensor-based diagnostic system, or we have easy remote access, so that we can directly look in the machine, not only to the control, but also to the sensor very deep in. So I see there is a very high potential also to install this system in the easy way. Here is the state-of-the-art monitoring system. That is our so-called Genio Modular. We have some here some base module is connected to the control. That means this is to the machining center. On the one hand, we have sensor modules, and each sensor modules can connect it to different kind of sensors. So as we see, it's not only a vibration or acoustic emission sensor we want to connect. We see more and more there is a need for force sensors, because it's in a lot of machine tools very hard to implement these sensors. You can change the workpiece holder, but to go through with the cable through all the machines, that is a very hard approach. Yeah. So maybe you remember the slide. Here is closing the loop. We have on the one hand the multi-sensor platform or the acoustic emission sensor, and we can feed it back to the machine, yeah, to have a control loop, not only for monitoring, also for changing. Yeah. That is the idea we have here. For example, closed loop with GEM via the 5G network. We didn't have reached it, but that we are working on. We have this multi-sensor platform, AE sensor module. Then we have a MQTT client, because this MQTT is going through the mobile networks. Then we have a 5G base station and an MQTT broker, which gives back the signal. And that is now we are challenging with to have these, how to detect how fast we can run this. Maybe it's not always necessary to use wireless, but it makes it easier to make the cabling or also the algorithms to run via the 5G. The idea for this adaptive control is, in a very simply way speaking, the high signal, I have lower feed rate. So if I have too high loads on my drill or on my cutting tool, I reduce. And if I have low or no signal, I can increase the feed rate. Different signals can be used. For example, true power, torque, acoustic emission, vibration. True power, there's the adaptive control known, but it's not so fast. And in some cases, it gives not the reliable or good signal. So what we did here for the demonstration, hopefully I can show this in a few minutes. We have a GEM, a VA3D sensor in the machine. We have a GEM CPU as a MQTT client that is more a simulator. We have an internet accessible MQTT broker, and which the aim was to send it via the mobile network, but that was actually not working, so we have to cut it down, but use an internet MQTT broker, which is in our partner company or our part from MMS in Hannover, and we feed this back from the GEM 5G module and to the GEM CPU to close this loop. This is our machine. I can try to show it also. Sorry. That is a view in the machine. Here we have in the middle the milling head, which I will show. Yeah, I can make a look here. This is a laboratory here. We have a milling machine. There are some other machines, but that is our main. As you can see here, here is a control. That is a Siemens 840D. Here is a user interface. It's a GEM Visu, where we see the signals here. And when we go back here, here is an electric cabinet. It looks a little bit crowdy, but here, as you can see, here is a module with a 5G or actually 4G. And later we have here antennas. Yeah. So that is a test band. We have here different modules where we connect this. Yeah. So hopefully this will run now. Now, I think hopefully you can hear and also see the process on the left hand here. Here is a signal, and you can see here the adaptive control. That is the output, and it's now reducing the speed because I have very high vibrations here. Here you can see it changing between 70 and 130. Honestly, we must say the adaptive, the controller is not optimized. I think that is the next step we have to work on to make an optimization. It's a very simply milling here. This is not optimized from the NC programming, but it's for demonstration. And what you can see here now is very interesting. Now it's at the end of the program. In the last process, maybe you saw there was not so much cutting, and the controller was working with about 130% of the nominal or the program speed. That means I saved a lot of time during this cutting. So that is the economical benefit on the one hand. If you have optimized NC program for the mass production, normally that is optimized in itself. But if you have long time cuttings for the forming, or if you have long time cuttings over hours, then it's a big advantage. So here is an example. You saw the screens. And here on this slide, you can see the standard process was about 70 seconds. And if I detected here, I have an under measure or I have not so much material, I about with a 10 seconds here. So that is a reduction in that case, it's 40%. Normally, if you use adaptive control systems, you have optimizations of 5, 10%. Yeah. So in the conclusion, the adaptive control and chatter control application. As you can see here, we have easy adaptation of diagnostic systems. We have easy remote access via 5G with gap control, detection of workpiece and tool position. That is another use case we often hear from our customer. They don't know where exactly the workpiece is, and they want to easily mount some sensors on and then get the contact between the tool and the part. Then measurement in big machines. So you can see we have a lot of advantages to use this new technology. And what for us was interesting, even this control closed loop was not working through the 5G because of network connection problems, because we are in a very naturally area here. And but even if we use the internet to imagine we send the signals from Egestorf to Hanover and get the signals back via this MQTT, it was possible to set up a closed loop. And so we think with 5G we will have really more opportunities. So with this, thank you very much. And if you have some questions, please tell me. Yeah.
Okay, thank you very much, Dirk. Can you just stop sharing your screen?
Sorry. Yeah.
Okay, so I'd like to hand over now to Maike. So now it's time for questions and answers. So Maike, please.
Yeah. Hello, everybody. I'm a research assistant here at the Fraunhofer IPT, and I'm leading the QA now. And you have the chance to ask the questions to the experts. And I would like to have lift your hand if you have any questions, and I'll call you up. So yeah, I hope you have many questions and have fun.
So I think the chat function is not working for everybody, so just use the hand symbol in Microsoft Teams and
So I have one hand here from Gerd-Jan Hartog. Yeah, what is your question?
My question is, we've seen up to now sensor applications with acoustic emission. Are there any other sensors being developed in the 5G campus, like tactical probes or something that could be used in a tool changer?
For probes,
so maybe
So you can. Yeah.
Please, yeah, maybe. Yeah, the multi-sensor platform is actually a versatile approach. So this accelerometer is one example, but so the next generation that we are designing is actually capable to address many different types of sensors just by a universal SPI interface. So then a tactile probe could also be attached. So this was not the first idea actually, because tactile probe is not a typical wireless use case. So we go for this accelerometer. We go for temperature sensor, so to measure the temperature of the workpiece under process. Also, strain gauges will be attached to measure, for example, any bending of the parts during the machining, which is of course also quite crucial to know. But also we will integrate a microphone sensor, which then can be used for the machine condition monitoring. So imagine this sensor box being placed inside the machine, and then just to record what is happening inside the machine. So how do the motors sound? How do the bearings sound? and so on. So that's more or less about pattern recognition. But yes, the touch probe can also be used. Of course, touch probes are being also used wireless today with 2.4 gigahertz or infrared communication. But typically then the transceiver or the receiver is then also typically located inside the machine. And then mostly integrated with the PLC of the machine. And it's typically not possible, not thought about to have access to this kind of sensors from outside. So if you imagine this 2.4 gigahertz communication is just a point-to-point connection, and with the help of 5G, every sensor has its own IP address, and it's a completely different approach then, of course. So Dirk, do you want to add something?
Yeah, the touch probes are one thing. The other thing is the tool holders with strain gauges or workpiece holder with strain gauge sensors. What we see. And in the area of vibration, we often have the requirement they want to make test measurements, but don't put cables in the machine. So I think that is a very good use case for testing and investigations.
So the touch probe is actually indeed also a potential use case if you think about the scanning probe, where you typically follow the shape of the part during
exactly. With analog probing.
Right, and the speed of this interrogation, because the touch probe follows the shape, so it's actually a closed loop operation. And as long as you can decrease the sampling time or the interrogation time and have a reduced latency, and then of course the scanning can be faster, and if it's faster, then you can start to machine earlier, because typically the machine owners do not want to measure, they want to produce parts. And
yes,
so
but in the tolerance, that's the problem.
Yeah, exactly, yes, exactly.
Thank you very much. It was a very good
Yeah,
answer.
you're welcome.
So, do we have other questions? Yeah, I see one. That's Jürgen Otterer.
Hello, are you hearing me?
Yeah, I think we can hear you.
Yes, great. Congratulations for the presentations. I have a question that is related to the wireless network. Have you used any industrial Ethernet protocol on the wireless 5G network?
Niels, do you want to take it, or you want me to take it? Okay, I can take it.
You start, please.
Okay, yeah, we have been using different industrial protocols, and mostly out of the Profinet or ProfiSafe family. We have been trying those ones on both LTE and 5G, and have applied them to various control and steering applications. So direct Ethernet direct layer 2 communication has been tried and has been tested in proof of concepts here quite a few times. And if you happen to be at the Hannover Industry Fair, for example, last year or the year before, you would have seen quite a few of those live on the booth there.
Of course, from the OT perspective, we look very much at synchronization, because if you imagine having the sensor signal from the process, for this is also very important to know at which position during the machining process you actually have which signal. I'm talking actually about the mapping of the sensor signal to the position. This actually requires also to extract the machine coordinates which is possible. So there are different approaches. For example, this GEM modular from Marpos is actually one hardware-based solution that actually is directly integrated into the Profibus communication, then delivers these kind of machine data. But nevertheless, if you have a sensor which is actually sending into a different network, you need to synchronize these kind of these two data sources. That's this is something which we are looking at also in 5G-SMART, to have some synchronization solution both for the sensors and both for the machine. And of course, we are very much looking forward for the availability of TSN over 5G, which will then be, I think, another game changer.
Okay, thank you, Niels.
Okay, thank you.
There's also another question. No? Do we have other questions? Jürgen, I can see you again. Do you have another question?
Thank you. No, I now place my first question.
Okay.
Thank you very much for these nice demos and very good impressions here. Do you see from the acoustic sensors also some video sensors to be used in 5G-SMART?
Yes, that's also part of 5G-SMART, but not in at our trial sites. So we have 3 trial sites. There's one in Kista, Stockholm, of Ericsson and ABB, where it's also about cameras, video cameras, and robotics.
For robotics, okay, thank you.
I guess there will be a webinar at a later stage, so please keep updated and have a look at the 5G-SMART website or follow on Twitter or LinkedIn, then you won't miss it.
Okay, thank you.
So do we have other questions here? No, I can't see any.
Okay, so if
I
this is not the case,
that's not the
last
case.
chance. So some closing remarks then. So I hope you enjoyed this webinar and got some new insights, some new inspiration. And yeah, if you want to keep updated, then as mentioned, just follow 5G-SMART project on LinkedIn or Twitter. Or if you want, you can also follow the 5G Industry Campus Europe. So it's also updating on the achievements within the use cases of 5G-SMART, of course. So I found there was quite some insights. Also, thank you from Dirk. You actually underlined the economic factor of having the highest possible machining volume over time. So it's about creating chips, as many as possible in the shortest time possible. Of course, not sacrificing the quality. Of course, it's very important. Yes, and thank you very much for the participation. And hope you got some inspirations from this webinar. Thank you very much.